Okay, today let me start what we left from the previous lecture. From the previous lecture, what we have is chapter 6. Okay, for the chapter 6, there are three learnings objective, and typically this uh, chapter we have two big problem in the examination. That is going to be the first one. We require you guys to be able to draw the influence line diagram of the beam and the girder. And first, I suppose to start again, what is the influence line diagram? Influence line diagram is diagram of reaction or the diagram for the shear force or the diagram for the bending moment at a point. I should focus on at a point. For example, if we consider point A, okay, and then we have statically determinate beam or girder as this one. And then for the influence line diagram, we will put the unit force X on this beam. Let's say this beam has a length of L. When you set this, you set the reference line on the left, and you say this is X. S going to be from the left to the right. Okay, that is going to be the left to the right. And when we set at a point for this one, let's say at a point A, by doing this, we will have the free body diagram of this beam. Let's say this is A sub Y, this is A sub X, and this is going to be B sub Y. Okay, and then again, you're going to find the reaction this time at point A. You use what? You use first, use free body diagram, the same concept that I just saw it. Second, you use the equation of equilibrium to find the equation of this A sub y. We have a summation of m sub b equal to 0. Just take moments over here. And then you have the A sub y times L, that is A sub y times L. And then the distance here going to be L minus what? Minus X. And then you have this one equal to 1 times L minus X. And then you get A sub y equal to L minus X divided by L. That is going to be 1 minus X over L. And then by doing this, we draw the diagram in which we put the horizontal axis as the X. And then we put the vertical, this one as A sub Y. From this equation, X start to be 0 over here. And X gonna be L over here. And over here, X gonna be L over 2. If you set X equal to 0, this one gonna be the value of 1.0. And then if this one is L over 2, that is going to be 1/2. So 1 minus 1/2, this one gonna be 0.5. And if this is X equal to L over here, you get this to be 0. This is what we call it the influence line of reaction A sub Y. It shows the value of A sub Y when the 1.0 unit load applied at this X, and the value A sub Y here again, if you draw it, that is A sub Y, the coordinate here is 1 minus X over L. And then if you do the summation f sub y equal to 0, the b sub y plus a sub y equal to 1. And then the b sub y gonna be 1 minus a sub y, and then you can get this one to be x over L. Again, you know the diagram in which the horizontal gonna be x meter and the vertical gonna be b sub y. This time x equal to 0 is going to be here. And then x equal to L over 2 is here. And x equal to L is here. When x is 0, you will get the value of this to be 0, right? That is 0. And if x equal to L over 2, L cut L, that is going to be 0.5. And if x equal to L, you will get this one to be 1.0. Okay. And then you also use the same thing, the free body diagram, the equation of equilibrium to determine the inference line for shear force and also the inference line for bending moment. You may go back to the video clip that I given to you from the previous lecture. Okay. By doing this, it means is we can draw the inference line diagram in three ways. One, you can draw it by create the table. Okay, you move the x by, for example, 2 meters, find the reaction. You move it to 4 meters, find the reaction. You move it 6 meters, find the reaction. This is very cumbersome. Okay, and the second one is better by what? By derive the inference line equation by the equation. This one is better, but is still not that convenient. And the last one is by principle created by Professor Musler and Professor Besler. And we call this one is the Musler-Besler principle. I will talking about this later. Then the second, after you get the inference line diagram, the next one will require you to determine the loading pattern for the inference line diagram. For example, for this beam, the inference always positive. So for this one, if you have the beam there, you draw the beam again, and under the specific type of what so-called the dead load, and dead load is going to be divided into two things: dead load of point load and dead load of live load. Most of the time, no matter the shape of the inference line is, we just put the dead load for the whole beam, because the dead load that is uniformly distributed load is the cell weight of the structure. That means it's always full of this. And then there is another thing is the live load. Again, live load may be the point load, and live load may be the uniformly distributed load. The live load can be long, can be short. In this way, the positive full of the beam length. So by doing this, you may put this live load over here. I will talk about this later. And also, for example, you have the live load, that's to be the point load. For example, you have what? You have the weight of the pickup truck. That is going to be front wheel load and rear wheel load. By doing this, let's say this is 10 kilonewton, this is 8 kilonewton. You got to put what? You got to put the large weight into the position of large coordinate. And then by doing this, you just put this one for 10 kilonewton. and this one, let's say 2 meter later, this is 2 meter. You put this one for 8 kilonewton. This is going to produce the maximum A supply. Again, if you use this one, this has the positive also, and you can know the loading pattern of B sub y very similar to for the A sub y, in which the dead load is will is not is will cover the whole leg, and then the live load, that is uniformly distributed load, also the same thing. Since this is positive, all the leg just put this one like this, and then next the 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 point load in this way. We have one over here is maximum. So by doing this, we will put 10 kilonewton here, and 2 meter from here we put in 8 kilonewton. You can see this is going to produce maximum V sub y, and the loading pattern for the maximum A sub y are different from the loading pattern for maximum B sub y. So that is what you are going to determine. And then when you got this, the later you're going to ask you to draw the shear and moment diagram basis on the loading pattern that you have. That's for the first problem of this chapter. It will involve the learning objective 1 and learning objective 2. And the last one, the second problem of this chapter, to determine the absolute maximum shear and the absolute maximum moment. That's absolute is the maximum of the maximum, okay, for the beam and girder. This is really useful for the design of the beam of the girder for a bridge or for a crane structure. Okay, that is the first one that I should mention about this. And then come to the Mueller-Bessler principle. Heinrich Mueller and Bessler in 1986 has proposed when we like to draw the inference line for a function, for example, the reaction. Let me come to what we have, the reaction. Let me have the beam as before. This time I put this one for the pin. I put this one for the roller. And I say this is A and this B. I like to draw the reaction. Okay. At a given point, I like to draw the inference line of A, and then at point A, and then for the reaction A sub y. What I do is what? The inference line of the reaction at the point A is the same scale as the displacement shape of the beam. When the beam is acted upon by the function, that means the beam is going to act upon by the A sub y, in which that point has no capacity to resist the function. That means you release the support here, okay, and then you put the A sub y to move the beam. Since this is the pin, this is going to be the rotating point. You move it forward. You move it for a distance of 1.0. So this one moves to here. And then the movement of this beam going to be in the form of rigid body. So you get a straight line. And this is the inference line of A sub y. And then if you prefer to draw the inference line of B sub y, you just keep A the same thing. You must release the resistance to B sub y. That means over here is pin, right? It still have the resistance for B sub x, even though B sub x is 0. And then this one move to the unit of 1.0 to this point. And then you get this shape as the what? As the inference line of B sub y. And then for the shear and then for the moment, I will talking about this later. Okay, this is the main principle of this. That means we can draw the inference line diagram of the reaction by what? By first we take the support at A out, put the reaction A sub Y to that point A and move it one point. The shape of the beam that's checked is the inference line diagram. And again, we supposed to say by using the Moore service based law principle, the beam is assumed to be rigid beam for this kind of statically determinate. And the support that is in the roller is going to rotate. Okay, it's going to be the rotating point of the beam segment. Okay, and then we have a lot of examples that we supposed to check. Let me start again by show you the inference line diagram of a beam, and then we will discuss more later. Let me demonstrate. That's going to be the best way to learn about this. Let me check this one to, okay, this one. Okay, let's see. Coming into this, let's ask has a beam, and what we have is the beam that is statically determinate. Let me have this one to be like the beam. Oop. Okay, if this one is a very simple beam that we have it before, this is thin, this is roller, and then when we like to draw the inference line of this one, we put the load of 1.0 unit here, and then we set the reference x coordinate from the left and to draw the influence line diagram. What we going to draw is the diagram that is going to be first again reaction. Okay, second shear force. Third is going to be bending moment, and that will be at a point. At a point. For example, at the point of A sub y, at a point of B sub y, and you may if I see it for the shear force, this is A, B. You may put this one, for example, for the point of C, you may at a point such as a point of C. So it's going to be V sub C, and the bending moment of what? Of the point C is going to be M sub C. Let me start by this beam first. And what we going to do is we're going to use the Musler principle to draw it. Okay. By using this principle again, we just put this one into what we have, and then what if you like to determine the inference line of A sub y, we just what we just keep the point, let's say this is B, okay, at the same thing as before, the system roller, and release the resistance to A sub y. So this change to roller, and then you move this one up, okay, by the A sub y for what? For 1 unit. Okay, that is going to be 1.0. This is the rotating point. You get this one as the inference line of this, and the coordinate of this from the previous lecture, we get this one to be 1 minus x over L if the beam has the length, okay, of L. And then for the B sub Y, you do the same thing, but this time you keep the pin like this, and then you change the roller, you release the roller, and then you put the B sub Y to move it. This one gonna move for 1.0 unit, and you get the shape of this to be the inference line of B sub Y, and the coordinate of this is going to be x over L. Okay, and then come to the point C. Let's see if the length for A to C is A, and for C to B is B. Okay, from the previous lecture, what we have is what we going to consider point C, and in which what the point A steel pin and point B steel roller. We must first this one release A sub Y, this one release B sub Y. That means this one we are going to release the shear, and then you supposed to understand for the shear force that we have for the ending static. On the left is going to be downward, on the right is going to be upward. To release the shear, we just put the roller guide, we just put the roller guide to point C, and then this one apply A sub Y, this one apply B sub Y, this one we got to apply the positive shear on the left downward, on the right upward. When you move it, this one going to be the rotating point, so you're going to have this one to be this triangle, and the same thing you're going to get this one. And from the previous lecture, if you remember it, this is going to be in parallel, and by doing this you're going to get this one by equal slope, and this one is going to be what, this one minus A over L, this one going to be plus B over L, and you can check the slope here is going to be this one A over L, and the length from here to here, that is going to be the triangle is going to be A divided by A. So this one going to be 1 over L. The slope here also, if you measure this, it's going to be B over L. And this is what? This is the length of B. So you divide it by B. This is going to be 1 over L. Okay, that is the mass. And then you can see the height of this going to be what? Going to be A plus L plus B divided by L. That is going to be A plus B divided by L. A is here, B is here. The total is going to be L. This is the total going to be L over L, and it's going to be 1.0. That is the requirement by the Mueller-Basler principle that you derive from the previous lecture. Okay, and this is going to be used later. And then come to the moment at C. The principle is still the same, just keep the pin and roller at A and B, and at the point C you must release the moment, release the resistance to the moment. By release the resistance to the moment, we just put the hinge into it. Okay, and then we come to the sign convention from the ending static for the positive moment. We must put that moment into this one, and then it look like you open a door. So this point going to move. Okay, like you open the window, open the door, and then the shape of the beam is going to be like this. And this one going to be inference line of M sub C. And what you get is what? What you get is the length from here to here is going to be AB over L. Okay, this is going to be AB over L. And what we have is the relative slope from these two sides. This is going to be 1.0. Okay, if you not believe over here, you can find the slope here is going to be AB over L. This is going to be AB and it's going to be divided by A. So the slope in this is going to be B over L. This is going to be B over L. And the slope on another slide or here is going to be the slope is going to be AB over L. And it's going to divide by this length. It's going to be 1 OB. Cut. So you get to be A over L. This one is A over L. And the combination of them going to be 1.0. Okay. That is the way we draw the inference line of A sub Y. This is for the inference line of B sub Y. This is inference line of B sub C. This is inference line of M sub C. And draw is for what? Again, we draw it for finding the loading, LOAD, loading pattern. That's going to be produce what? Produce the maximum A sub Y or maximum B sub Y. Also maximum V sub C and the maximum M sub C. And Ajahn should say again that it's going to be maximum is depend on two kind of loading. That is dead load. Dead load is simple, it's always there. Another one is going to be the live load. Live load going to change the position as it should be based on the shape of the inference line diagram. Okay, and then again, it's supposed to say that the live load to be live loads of the concentrated force or point load, and the live load for the uniformly distributed load. And the dead load also have a dead load of the point load and the dead load of uniformly distributed load. Let me start by checking of this beam in which we have the inference line of this is going to be all positive. And again, I should say that for the dead load, whether you provide it in anywhere is the weight of the beam. So it's always in the full length of the beam. Okay. And if it have the dead load, that is the point load, just put it there. That's the given one. That is the same one as you use to draw the shear diagram and moment diagram. And most of the time, we didn't much consider this. But for the live load, the one, this is going to be the full length, okay, of this one. And what we have is what? What we have is distribute the whole influence of this. And another one, if you have the point load and it is the weight of the pickup truck, let's say it's like 10 kilonewton, and this is 8 kilonewton. And since this is large of 10, you got to put it over here. So for this one have 2 meters, for example, but 2 meters different. You just put this one to be 10 kilonewton, and by 2 meters, you put this one for 8 kilonewton. That is the shape of the load that produce the maximum. This is going to produce the maximum A sub Y. Okay, and for the B sub Y, I show you again already, but I'd like to show you for the V sub C, and you can see B sub C have plus and minus. Okay, and you can see the area of this positive is larger than the area of negative. So the influence of positive area is more than influence of negative area. Okay. By doing this, the loading pattern can be done like this. Just put the dead load. Okay. If there is a dead load, just put the dead load along the length of the beam. And then how about the live load? This time the live load will not put in the negative area. We just put it in the positive area because it has the larger influence. That is about 3. Just put this one to be 3.1. Okay, this is going to be the point of C. That means the live load this time will be just between C and B. Okay, because if we put it in the between the A and C, that's going to produce the negative, okay, influence to the shear at this point C. And how about this? The maximum is what? The maximum is here. So we just put the 10 kilonewton here, and then we put the 8 kilonewton here. That is 2 meters different. Okay, you can see they are different. It depends on the shape of the influence line. Now we move to the M sub C. For the M sub C, again, what we have, they are positive. That means what? That means for this beam, the live load, both live load, that is uniformly distributed load, and dead load, that's uniformly distributed load. They are going to be the same. It's going to cover the whole length of this beam. And why? Because it's always positive. What we have next is the live load. That is the point load. So what is the maximum? Again, we put this one to be here, 10 kilonewton. And then you may select to put the 8 kilonewton. And I believe if we put it in this way, it's going to be produce the maximum M sub C. Okay, and then you can see the loading pattern that's used to produce the maximum A sub Y, maximum V sub C, and maximum M sub C. They are different. Okay, and we will talk a lot about this later, but I should focus that how do we determine the value or magnitude of maximum A sub Y. Okay, let's say if I put the L is going to be 20 meter and I put the A to be 5 meter, the B is going to be 15 meter. Okay, by doing this, I should pinpoint one thing. The point load can be determined from what? The point load can be determined from the magnitude of the load, the magnitude of the load, and time what? Time the coordinate, okay, at the loading point. Loading point. That's the way we determine it. For example, let's say for this one, what we have is going to be if the dead load is going to be 1 kilonewton per meter, and the live load is going to be 2 kilonewton per meter. Okay, and then this is 10 kilonewton. This is 8 kilonewton. Let's say for the A sub y maximum maximum A sub y from what? From the point load. That means from the 10 kilonewton. So you got to be what? 10. You got to be the value of the 10 kilonewton times the coordinate. This is going to be 1. So it's going to be times 1 point load. That is coordinate at the loading point. And then we plus this one by what? By 8 kilonewton. By 8 kilonewton. And 8 kilonewton is what? Is 2 meters from here. So this is going to be 1 minus 2 divided by 20. That is going to be 0.9. So that is going to time 0.9. That is the A sub y come from the point load. And then there is what? There is the uniform load. The live load W and also dead load W. You can determine it from what? From the magnitude of the load. And then it's going to time the area of influence line diagram B between the live load, that's uniform load, or dead load, uniform load. What I mean is this is going to be the value of this, the same thing. That's combination of them is going to be 3, right? So this is going to be plus 3 kilonewton per meter, and it's going to have the area. This area is over the whole beam. So this is going to be 1/2 of 20 meter and then times 1. So this is the contribution of the uniformly distributed load. That is going to be what? This is going to be 10 plus this one is going to be 7.2, right? Yeah, this is 2, and plus this one is going to be, this is going to be 10, and this is going to be 30. So you get this one for 47.2 kilonewton. That is going to be the maximum. That is going to be the maximum of the A sub y in this case for 47.2 kilonewton. Okay. And you also use this same method to determine something else. Okay, let's say if you like to find the maximum of what? Of V sub C. For the maximum of V sub C here is, this one is going to be, very complicated, right? Yes, because that is positive and that is negative. Let's say what we have for the positive is here. Okay, and what is 10 kilonewton? That is 10 kilonewton. 10 kilonewton gonna time the coordinate here. That is going to be V over L. That is going to be 15 divided by 20. That is going to be 15 divided by 20. And then for the next 2 meters, you have 8 kilonewton. So you pass this one 8 kilonewton. What the coordinate here? Okay, this one 15 divided by 20. What you get is going to be 304, right? 15 divided by 20. This is, no, sorry, 15 divided by 20. That is going to be, divided by 20. Yeah, 304. That is going to be 0.75. And since this is 2 meters from here, and you will have this one to be 0.75 and divided by this one divided by 15. And then this is going to be the y divided by what? This is 2 meter. So this is going to be 13 meter. So you got the y. Okay, to be 0.75 times 13 divided by 15. Okay, times 13 divided by 15. That is to be 0.65. This one is 0.65. This one is 0.75. They are positive. We succeed. And then there is what? The combination of this dead load, that is, and live load is going to be 1 plus 2 equal to 3 kilonewton per meter. Okay, next we plus this one by again 3 kilonewton per meter. However, the area is going to be 1/2 of what? Of 7.75 times the length here is going to be 15 meters. And not enough of that. This time we have this one. This one gonna be produce the negative effect into the V sub C. You got to minus this one by what? This one is the dead load, right? Dead load. And then dead load is 1 kilonewton. That is going to be 1 kilonewton per meter, and then times what? 1/2. This is A is 5 meter times 5, and this is A over L. That is going to be 5 over 20. That is going to be 0.25, and this is going to be the value of maximum V sub C. So this is 7.5. This is 7.5 and 8 times 0.65. That is 5.2. This is 5.2, and this is going to be 1.5. This is 1.5 times 0.75 times 15. That is going to be 16.875. This is going to be 16.875. Right? Yes, 1.5 times 15, 1.5 times 15 times 0.75. Okay, that's great. And the last one is the negative. That is going to be 2.5 times 0.25. That is going to be 0.625. And then you combine this together, 10.875 plus 5.2 plus 7.5, and then minus, this is pretty small, right? 0.625. You get it to 22 point. This is 22.95 kilonewton. This is in kilonewton, okay? And the shear is here. For the moment, you do the same thing. This is going to be the maximum of what? Of M sub C this way is going to be the force here. The force here gonna have the total area here, and the 10 kilonewton gonna have the coordinate here. The A is going to be 5 and B is going to be 15 and divided by 20. So that is going to be 15 divided by 4. That is going to be 3.75. Okay, this is going to be 3.75. This is going to be 3.75. Again, we project this one to find the coordinate here. Y over here divided by here divided by 13. This is 15. This is 2 meters. This is 13 equal to 3.75 divided by 15. So the y here is going to be 3.75, and times 13. divided by 15. That's 3.25. That is going to be 3.25. That is going to plus 8 kilonewton and times 3.25. Okay, that's for the point load. And then next we have the the force here. The combination of them is 3 kilonewton per meter, and then you times this by 1/2 of this one for 20, and this one for 3.75, and then you will get what we have. This is going to be plus, and this is going to be in the unit of kilonewton meter. What you have, just do this. This is going to be 3.75, and then 3.25 times 8. That is going to be 26, and this is going to be this is 10, 30 times 3.75. This is 112.5. So you plus 26 plus 3.75. You get this one for 142.25 kilonewton meter. Okay, this is the way we determine what we have here. And I like to mention about something after you get the shear here. What we have is going to be the free body diagram, okay, of this one. That is going to be A sub y, and this one gonna be subjected to the 1 kilonewton per meter. And what we have here is this one is going to be 22.95. So that is going to be the shear here, and then is positive. This is 22.95 kilonewton. Okay, and for this one, if you do this one again, you also have this one for A sub y. Oh, sorry, you also have M sub c for this one also. And for this one, you have the load here, and then you got the moment here. Oh, this is 142.25 kilonewton meter, and you get this one for V sub c. And in each case, it will produce the value of M sub c and V sub c differently. Okay, because the loading pattern are different. Okay, this is simple, but it requires some understanding. I like you guys to go through all of this to review them. Okay, in order you guys to understand this thing in depth. Okay, and then come to what I have over here. Let me come to this problem again. There is beam, and then this beam we made a lot of inference line diagram. Actually is not just for the A moment at A, shear at B, reaction at C. Let me go a little bit further. Okay, by drawing the inference line of reaction first, and then going to find the inference line of shear force, and then going to find the inference line of moment. Okay, let's see what kind of this beam. This beam is the statically determinate. Okay, to check it, you can see we supposed to check the unknown of this beam. Okay, this beam has the fixed support at A. That means at A we have the shear force, the bending moment. We have the bending moment M sub A. We have V sub A. We also have N sub A. Okay, and it has the roller SC. That means SC is has this one for C sub y, and it has the internal hinge at B. That means at B is going to have two more. So the unknown is going to be 3 plus 1 plus this one going to be B sub x and B sub y plus 2. That is going to be 6 unknown. And what we have the number of equilibrium equation. We have what? We have 2. And since the segment of the beam is n equal to 2, so this has the number of equation equal to 6. So this is going to be statically determinate beam. Okay, just check it first. And they said we are going to draw the inference line of M sub A shear force. This is the moment A, shear force SB and reaction SC by using Hopper scale. Let me a little bit working on this. Let me start by drawing the inference line diagram of A sub y first. That is going to be a little bit more proper. Okay, just draw it. We are going to draw the inference line diagram by using this kind of complex beam, by using the Musler-Bresler principle. Okay, we will use this again. And by doing what? By doing this, you're going to draw the inference line of A sub y. What you do is this C is going to be the same. The B is going to be the same. Now you release what? You release the reaction at A. So what we have is this one still be the beam. And then to release that, you got to put the roller guide. Okay, you put the roller guide. This roller guide has no resistance. Now you put this roller guide, no resistance to what we have, what A sub y. So when you do this, that means on this side it won't have resistance to A sub y, but it still have resistance to M sub A. And then you push this one up by the force A sub y. What it moves is it's going to move this one for 1.0 unit. This is going to move for 1.0 unit. What is happened if this 1.0 unit is going to be something here? No, it cannot be something here because it has the joint, it has the hinge here. This is the hinge. Okay, when it has the hinge here, this one gonna move in the way like this. This one going to move up like this, and this is going to be the inference line of A sub y of this one. When it moves up like this. Okay. And then if you like to draw next inference line of, let's see, C sub y. Okay, this is also the same one that we have reaction at C. That means what? That means we still keep the fixed end here fixed. Okay, and what we have, this one is going to be the hinge, and we release, we take the roller out, we put the C sub y to move this one for 1.0 unit. Okay, when this occur here, this is going to be the rotating point because this portion fixed here. So by doing this, when you move, this is the rotating point, is going to move something like this. Okay, so the shape of inference line of C sub y is going to be something similar to here. Okay, so we run out of the reaction, right? Yeah, the M sub A we will talking about later. It's okay. Just put the inference line of the moment at A over here. Okay, the moment at A is also the reaction inference line of M sub A. Okay, and just put this one over here. Let me put this one in the back. Okay, so it's going to go together. Okay, what we have is by doing this, the hinge here is okay, the roller here is okay, but over here is used to be the fixed end. When you're going to draw that moment at M sub A, you got to release the resistance of M sub A by putting the hinge into this point. And then not enough, you also put the moment M sub A at, at this point. What happened is this one produce nothing because it acts at what? At the wall. So over here they're supposed to rotate. When it's rotate, the relative is going to be have 1.4 slope. Okay. And then if this one is 5 meters and you measure it to be about 2 centimeter, 2.1 centimeter. So this one gonna have 2.1 centimeter downward, okay, to make it on scale. So we have the inference line of M sub A in this shape, okay, is part of the inference line for the reaction. Okay, reaction can be both forces and moment. Okay, and then we go further to the shear, okay, and let me put a little bit more simple. Make this one to be the point D. This one, a half of this. It's going to be, this is going to be 1, 2, 3, 4, 4.4. Okay, let's see. Half of this is going to be point D, and this is 5 meters. This is 5 meters. To make it a little bit more convenient, just make it by half. Let's say we have the inference line of shear at D. Okay, by doing this, what we have the point, the red one, the point C the same, the hinge is the same, and we have this one as the fixed support. And when we like to draw the inference line of shear, we just what? We just take the resistance for the V sub D out by putting the roller guide to this. And then what we have, we put the shear, positive shear that we have on the left is downward, on the right is upward. So this one gonna be downward shear V sub C, and this one gonna be the upward shear V sub C, and this one gonna be the distance of A. Okay, and the total L change to here, and this one gonna be B. So we have this one for minus A over L. That is minus 5 over 10. That is minus 0.5. So by doing this, just put this one for half centimeter, and this hinge going to be the rotating point. You get this. And this one also is going to move for plus V over L. That is 5 over 10. That is going to be 0.5. Just put it here. This is the rotating point. You get this one for the inference line of what? Of V sub D. Okay. And then you still have another thing. Just put this one in a half. Again, put it in half. Let me put this one in a half and set this one to be the point E. Okay. And now I just let me put this one, the shear at E, inference line of V sub E, inference V sub E. And let me put this one, okay, into this one. We don't have much area here. For the V sub E, the A still fixed and the B still hinge, the C still roller. What we have is we just cut point E and remove the resistance to the V at E. And then we put the V sub E positive to apply into this one. What happened is the V sub E that act here, the V sub E here, the force here cannot move this portion because this is fixed. So by doing this, only this portion will be moved for 1 unit and is moved up and it's going to be parallel to this, and the value of here going to be 1.0. This one also 1.0, very similar to this one. Okay, and this one going to be the hinge, and then the shape of this gonna follow on the on the A sub y. We have this one for the inference line of V sub E. Okay, and then let me have the inference line of the moment at E. Okay, just put the moment, just put this one, B the same, C the same. If you like to draw the inference line of M sub E, you just put the hinge here, and then you put the moment M sub E into this. Again, this is rigid body. The moment here cannot move this piece. Okay, only this one gonna move this one down. This is going to be 2.5 meter, right? So this one gonna move to be how many centimeter? This is about 9 millimeter. This is going to move into here. And since it's 2.5, it's moved by the angle of 1.0. And what we have is what is going to be minus 2.5. And then you just connect this one. Okay. Oh, sorry. This is 5 meter. This is minus 5. Okay. This is M sub E. And then if you like to do a little bit further, let's say you have the inference line for the moment at point D. Okay, we don't have moment at point D yet. Just put this one into what we have. Okay, this is going to be the same. It's going one change, and this hinge going to be the same. This roller going to be the same. You got to draw the inference line of M sub D. Just release the resistance to the M sub D. Okay, and then put the moment M sub D to move this one up, and this one gonna move to A times B divided by L. And by doing this, this is A, this is B, is going to be 25 times this one, so, sorry, divided by this one 10 is going to be 2.5. Okay, if you said this is going to scaling like half of this is 12.5 millimeter. This one gonna be this one. Let's see. Okay, about this. Then you have the shape of M sub D like this. Okay. Okay. You have a lot of things to draw the reaction, the shear, and the moment. Okay. And then what they have is said, if a uniformly distributed dead load, okay, act into this 1.5 kilonewton, the dead load 1.5 kilonewton, and a concentrated live load, the dead load is very easy. Let me change this one a little bit. If we don't draw it, let's change this one to live load. So it can it can adjust itself a little bit easier. And then they ask us to determine the maximum moment at A. Okay, which one? This one. Okay, moment at A. We have this one for 2 and 6.5. Let me have this one 2 and 6.5. Okay, let me put this into position, and this is going to be our beam, and this is fixed end, this is hinge, okay, and this is going to be the roller. This is A, B, C. Now you can see the influence of this always negative. So even though it is the live load, even though it's live load, the load acting over here will be go across the length of this beam because all of them produce negative. Okay, and then what we have is what we have is we just put the 10 kilonewton, and since this one is the maximum, so we put the 10 kilonewton into this one. This is 10 kilonewton. This is going to be 1.5 kilonewton per meter. This is 5 meter. This is 10 meter. Basis upon this, maximum M sub A is going to be what? The 10, remember, 10 kilonewton. And 10 kilonewton, gonna time what? The coordinate here, that is going to be minus 5. And then what we have is the uniformly distributed load. So we plus this one by 1.5 kilonewton per meter, and then it's gonna have 1/2. The length of this is going to be 15, and then this is going to be minus 5. Okay, and you just put them into your calculation. You supposed to get the first one, that is going to be minus 50, and this one going to be minus what? 1.5 times 15 times 2.5, that is 56.25. 56.25. So this is going to be 106.25 kilonewton meter. Okay, let's do the calculation of this. I think it's going to be correct. Okay, and then a little bit later, you determine next the shear force at B. We have the M sub A already, and shear force at B, V sub B. Oh, we didn't draw the inverse line of V sub B yet. Okay, don't worry. Just put the inverse line of shear force at point B. Okay, let me put it over here. V sub B. Just put it over here. We have this one for the fixed, and this one for the roller. Okay, this one for the roller. And then what we have is the point B is here. We're going to draw the influence line of V sub B. What we have is B is here. We need to release the resistance to the shear force here. So the hinge must change to be the roller guide, and then we apply the shear. The shear one is downward, that is V sub B, and another one is upward. What happened is again this one cannot move because it is fixed. Okay, because this is fixed. Okay, when this one won't move, so what we have here, this one supposed to move for 1.0 unit, and when this one move for 1.0 unit, what happened is the influence line diagram of this one will be okay to be this. This is going to be the positive. Okay, by this way, and then we do change the beam by using the live load. So the influence of positive will control the beam. So we have this one as the hinge, this one for the roller, and this one for the fix, and the live load now will span between B and C. So this one will have the load span in this one since they are the live load. So this is what? This is going to be 1.5 kilonewton per meter. How about the 10 kilonewton? The 10 kilonewton again is the point load. It's going to act at the point of maximum coordinate. The maximum coordinate is here. So this is going to be the point of 10 kilonewton. And then we have maximum of V sub B equal to 10 kilonewton. And this 10 kilonewton times this one times 1.2. And then the area here gonna have this 1.5 plus, they are positive, plus 1.5 kilonewton per meter. And then it's gonna have what? It's gonna have the area here. That is going to be 1/2 of the length here is 10 meter times 10 and times 1. Okay, so this is 10 and this is gonna be 0.75 and this is times 10. This is going to be 17.5. This one is going to be 17.5 kilonewton for the maximum of the V sub B. Okay. And then they ask us to find another thing is the maximum of the reaction at C. Where is the maximum of reaction of C? C sub y. Okay, C sub y is here. Yeah, C sub y is here, and then you see this is always positive here, very similar to this, but in the opposite direction. So the 10 kilonewton will act in different point. This is act at B. This is supposed to act at C. Okay, and then what we have again, just draw the beam. Again, just draw our beam. This is going to be the B is the hinge, and this is going to be the fixed support. This is going to be the roller, and then this is the positive influence. So we just put the uniformly distributed live load. I just change it a little bit into this, and this is going to be 1.5 kilonewton per meter. However, over here we got to put the 10 kilonewton here. So the maximum of what? Of C sub y equal to 10 kilonewton and times this point 1.2, and then plus this is 1.5 kilonewton per meter and times the area here. Area here going to be the same as here, 1/2 of 10 and times 1. So the maximum C sub y is going to be 17.5. Okay, 5 kilonewton as what we have for the maximum V sub B. Okay, this is a kind of example of the of the uh, of the uh, examination, and I can do something different by putting uniformly distributed dead load into this problem with 1.5. If there is another 1.5 kilonewton per meter dead load, just put 1.5 across all the beam and do the calculation. It's not that hard. Okay. Okay. So maximum moment at A is what? 106.25 kilonewton meter. And maximum shear at B is okay here, 17.5. And maximum reaction also 17.5. Okay, you can answer this easily. That's not hard. Okay, just change what we have here a little bit to make things different, so you can see what happened. Okay, let me show you something in the PowerPoint. You just remember this one, this beam fixed on the left, roller on the right, middle is hinge. Why Ajahn have this one? Don't worry. We has the example in our PowerPoint. Okay, like this one. Actually, I teach you senior by this figure, and I just change to the one that I just show you. Okay, so for this one, you guys can go through all of the video clips, okay, and do the inference line diagram and draw the inference line diagram of reaction of shear force of the bending moment. And then later, just put the dead load or the live load that's given to you into the inference line diagram and into the beam and do the calculation to determine maximum value of different things. I still have one more problem, okay, for you guys. Let me switch back to something else. For this one, you guys can go to all of this by your again. If you again cannot understand it, just go to the video clips that I have in the YouTube channel. Okay, that is one interesting example, and just compare to what I have shown you from the previous example. And let me come back to review again about the loading pattern. The inference line diagram, the good thing, we can use it to determine the loading pattern. When you finish drawing the loading pattern, we got to compute the maximum value of the reaction of the shear at the moment. And again, I suppose to focus if there is the point load, okay, the value of reaction, the value of shear, and the value of moment will or can be determined from what? When the beam is acted by the point load as the location, okay, of the unit load. No. The value of function due to the force F will be the multiplication of the inference line coordinate and the magnitude of force F. This is the magnitude. This is the inference line coordinate. You got to multiply. Okay. When the beam is acted by the force F. Okay. Let me take this thing out. Okay. The value of the function, maybe the reaction, maybe the shear, and maybe the moment due to that force is the multiplication of the coordinate of the inference line with the value of F. Okay, like this one. If I have a beam, my beam has subjected to the point load of 10 kilonewton at the coordinate x equal to 8 meter. If we like to determine the a sub y, we find the coordinate 0.6 and then we times 0.6 with 10, we get the r sub a equal to 6 kilonewton. What we have is this one is 6 kilonewton. Okay. If we like to determine it due to the 10 kilonewton, the reaction B R sub B, reaction R sub B is going to be 4.4 kilonewton. We can prove this one easily. Summation of the moment at A equal to 0. We will have R sub B times 20. Okay, we have this one positive 20 R sub B equal to what? Equal to 10. Equal to 10 and times 8. So R sub B is going to be 80 divided by 20. So it's going to be 4 kilonewton. And then summation of F sub Y equal to 0. R sub A plus this one plus 4 kilonewton is going to be equal. Upward is positive. It's going to be equal to 10. So R sub A is going to be 6 kilonewton. So you can see by using the inference line diagram to determine the reaction from the point load. Okay, is the results. The results are equal to what we compute by using the engineering static. Okay, we are using the free body diagram and the equation of equilibrium. Again, for the point load, you time the point load by the coordinate of the inference line. And then come to next, if we have shear also, this one is what? This one, the force time the coordinate. So for the shear at section 1, the shear x1 will be equal to 10 times 0.6. What I have is under the force there, and if you remember, we got what? We got the reaction A sub y of 6 kilonewton. And then if we consider this free body diagram, we will have this one for M1-1. And we also have this one, V done 1-1. If you use the summation of F sub y equal to 0, downward is positive. This is 4 meter. So V1-1 is going to be downward, 6 is upward. That is 6 kilonewton. So I can prove it. For the moment, again, that is going to be 2.4 and time F. That is going to be 24. Do just summation of the moment equal to 0. This one is positive. M1-1 is going to be 6 times this distance 4. That is also 24 kilonewton meter. So proof. Okay. No matter its reaction, no matter its shear, no matter its moment, you do the same thing for the point load. You time the magnitude of the point load by the coordinate of the inference line. Okay, you got the same thing. For the uniform load, again, there is two things. uniform load with dead load. This one going to put across the length, along the length, along the length of the girdle. And for this one, this is not. This is depend on the shape of the influence line, and this is going to be depend on the area of influence line. The area can be the area positive or area the negative of the influence line. You use we use the area positive or negative with the maximum area that's going to control or influence what we are determining. And then for the beam act by a uniform load, okay, along the length of the beam is depend on how long it is. The value of the function, maybe the reaction, the shear moment due to uniform load can be determined from the multiplication of the influence line area, okay, under the load W and time the magnitude of the W or is equal to, for in short, area of influence line between the force W and time what? And time the magnitude of W. And then this one you can show this one. And then if you have the the uniformly distributed load only in the portion of this beam, you just time what? This is A sub y. A sub y gonna time 10 kilonewton per meter time this split area. Okay, that means 10 kilonewton meter time area 1. Area 1 is 1/2 time 12 and time 0.6. Okay, then half time 12 time 0.6. This is 36 kilonewton. Okay, and you can prove it later. And for the R sub B, you time 10 kilonewton per meter by this pink area, this area 2. Okay, this is going to be 84. So this is 84. And then if you summation of f sub y equal to 0, you can see 36 plus 84 equal to the magnitude of applied force. That is going to be 10 kilonewton meter. This is going to be 12 meter. So the summation are equal. And the same thing, okay, you can check for the shear force and for the bending moment. Okay, and go back and try to check it. And then later, if you do this, you also can use this one to draw the shear diagram and moment diagram also. I would left this one for you guys to practice because this one you have it before. And then let's see, for example, for a very simple example, we have still have some time. The influence line for shear V sub C. This is influence for shear V sub C. This is minus A over L. This is going to be minus 2.5 divided by 10. Okay, this is going to be the value of minus 0.25. This is plus B over L. This is 7.5 divided by 10. This is going to be 0.5. And this is have the maximum influence. So for the live load, that is the point load. We got to put it in the maximum value of this positive influence. And for the uniformly distributed live load, it can be depend on the length. And since this is the maximum influence, so we have this loading pattern, and we can determine the 2 kilonewton times this pink area. For the 4 kilonewton, 2 kilonewton per meter, that's uniform load times the pink area. So times the yellow area, sorry, and then 4 kilonewton times 0.75. Okay, so coordinate is going to be 0.75. The area going to be the yellow area, and then you get this one for 8.625. You can verify it easily. And for the inference line for m sub c, just put everything and lift it up for a b over l. That is 2.5 times 7.5 divided by 10. So this is the inference line of m sub c. This time, the 2 kilonewton per meter will span along the length. And the point load gonna time over here, gonna point over here. So we have the m sub c in this way. Okay, and then whatsoever the previous slide or this slide, I just ask you to go back and draw the shear diagram and draw the inference line diagram basis on what we have here, not basis on the in static. You can use this m sub c. Okay, m sub c. If you know this, what I like to expand to you is this beam can be separated into two pieces and is subjected to the force here on this one, and then you got the moment act upon this. This is going to be 26.25 kilonewton. Okay, and what we have is we're going to have the shear V sub C here and the shear V sub C here. If you cut it, okay, just before the C, so the 4 kilonewton will act here, and this is 26.25 kilonewton meter, and then you can use this one to determine A sub y, and you can use this one to determine B sub y. Okay, when you know the reaction, okay, you can find the shear, and then you can draw shear diagram. You can draw the moment diagram basis on this. Okay, let me demonstrate to you on the next problem. We have about 20 more minutes on this problem. Let me switch this one to what we have. Okay, come to this problem. Again, if you check, the beam here is going to be statically determinate beam for sure. Okay, how many unknown? That is going to be this one, 2, 3, 4, and 5. Unknown, going to be 1, 2, 3, 4, 5. And then there is the connection. This is going to be 2. This is going to be 2. So the total is going to be 9. And what is the number of equation? Number of equation, we have 1, 2, 3 pieces. So 3 times n equal to 3. So it's going to be 9. Statically determinate beam. Okay. And it said ABC is the roller and D is the pin. Okay, this is the roller pin. And hinge at E and F. Draw the inference line diagram of reaction of the shear and the bending moment by using a proper scale. Okay, let's start by inference line of A sub y. By doing this, what we have previously, this keep to be the pin, this still be the roller. This is the roller. Just put the hinge Just put the hinge into it. Just put the hinge into it, and then we just what we put the we release the support out, and then we apply the A sub Y. We move this one for 1.0, and when we move this one for 1.0, you can see this portion of the beam cannot move. Only this one can move. So this is the inference line of A sub Y. And then next, inference line of B sub Y. Just release the what? The sorry, the resistance. Just take this support out of B sub Y out. So when we move to that, what we have is we release this one out, and then we have the B sub Y F. We move this one for 1.0 unit. Again, this one cannot move, okay, because it have two support. We can move. Then this one will go like this. How about this one? This one free to move. See, this one free to move, right? We move what? This one you're supposed to be moved together as a piece, because this portion of E, B, and F, they are the portion of the beam. And then when this one like this one gonna be the length here, this one gonna be 2.0. And we have this one for the inference line of B sub Y. Okay, I should mention this one is a piece of A, E. This is a piece of E, B, F. When we consider, we got to consider it as a piece. Okay, we consider this one as a piece. Okay, and then we have another piece is going to be FCD. That is three pieces of the beam to make it clearer. And then inference line of C sub Y, this one gonna be the same. And then B gonna be the same. And A gonna be the same. And just keep this one as the pin. And we gonna move this one by the force of C sub Y. By the force of Y for what? For 1 unit is going to be up over here. And since the pink, they the same piece, so they're gonna move together to be a piece like this. And then what we have, this one going to be the hinge. And then when this one hinge, this portion gonna move together. This one gonna be this green piece. And the last one, this is going to be the rotating point. And then we have this one for the piece of AE. That is inference line of C sub Y. Okay. And then they ask us to find the inference line of D sub Y. D sub Y is here. So we must change the pin into the roller like this. And then the C the same, the B the same, the A the same. And just keep this one as the hinge, this one and the hinge, and the hinge. And then you push this one to move in 1.0 unit. And then when you push this one, this piece, this segment gonna move together again. This is going to be the pink, okay? And this is going to move together. And this is going to be the green. This is going to be the green. And then this is the eternal hinge. When we going to have this one to be the yellow. Okay. Now, what we have is the top portion. Since this is 1, okay, divided by 5. This is y divided by 7 equal to 1 divided by 5. So this one going to be 7 over 5. Okay. And since this one is 3 meter, this one is 3 meter, this one going to be minus 7 over 5. So the coordinate of this one can be computed by similar triangle. Again, for this one, we have, let's say, y divided by 2 equal to 1. 1 divided by 5. So our y is going to be minus 2 over 5. Okay. When this one is minus 2 over 5, this one gonna be plus 2 over 5, and this one is 0. Okay. And then come to the g. We have the point of g. Point of g is here is 2 meter and 3 meter. Come to the inference line of v sub g. This is 2 meter and this is 3 meter. Keep this one the same thing. Just put the D, the C, the B, the A, and then still this one is the hinge, this one is the hinge. What we have is what? Inference line of V sub G. We release the resistance to the V sub G. And then we apply the positive V sub G to move this one. When we move this one, so this one gonna be moved up. And by doing this, we will have this one A equal to the distance here due to this one 2 meter, and this one B equal to 3 meter. So this one gonna be 3 divided by 5. That is going to be 0.6. Okay. And this one going to be in parallel to this. And since it's going to move in the same piece, okay, this one going to be minus 2 over 5 minus 0.4. And they are going to be parallel. And this what we have is going to be the pink, okay, and this is the rotation. Since this is 2 meter, this is 2 meter, 2 meter and 2 meter, this is going to be plus 0.4. And then this piece is going to move together at the green one, just move together. And then we have this one as the rotating point. This one 3 meter, this one 3 meter minus 0.4. And the last one gonna be this one, and put it in the yellow. Okay, this is the inference line of V sub T. And then we go a little bit further to the inference line of M sub E. What is the E? The E is going to be point here. Okay, this is point E. This is point E. Point E. Point E is what? Point E. Let's see. Not point E. Let's see. This is point B. Because point E is hinge. If we draw the inference line of point E, they always 0 because E is hinge. Inference line for the M sub E is 0. Okay, but inference for M sub B are different. So this is B, this is A, this is C, and this is D. Just put this one. Okay, the hinge, inference line for the hinge always 0. So what we have is inference line for M sub B. Just put the hinge here and put the moment, okay, on the left and on the right moment M sub E. And then what we have is what? What we have is what? This one, can it move? Okay, this one cannot move. It's a piece of this. Okay, this one cannot move down because this portion won't move. Since this portion won't move, since this portion won't move. Okay, this portion also won't move, and then the moving portion is going to move for 1.0 unit, and then it's going to move to here. And since this one is 3 meter, this one going to be -3. And we have the inference line of this one to be like this. This one going to be the inference line of M sub B. Okay, it's going to be a little bit tougher. For the inference line of M sub G, okay, again, G is here, and what we have is this is the same, the same, same, and uh, the hink still here, the hink still here, and we need to release the resistance of the moment at G out, and we apply the moment M sub G into it. This is going to move to here with the AB over L. Now A is 2, B is 3, L is 5, is going to be 6 over 5. Okay, and this one gonna be in this portion, and this one gonna be in this portion. This is the hinge, and then the pink will have the shape like this, and the portion of this gonna be moved in the same piece, and this is the hinge. We just connect them together. This is going to be the yellow, and this is going to be the green. And now the coordinate of this, since this one is 6 over 5, this one gonna be -6 over 5, because yeah, this is 2 meter, okay, and this is 2 meter, they are equal. And since this one is 3 meter, and this one also 3 meter, so this is plus 6.5. Now, can we put the load onto the beam again? Let's see. We like to find let's see, this one for C sub y. This is 8.5. 8.5 meters. Okay, just let me put this one. This is going to be our beam, and then what we have is this one is the roller. This is going to be the pin, and this is the hinge 1 to 2.8, 2.8, and 3.9, 2.8, 2.8. That's it. The pin, and then this is 3.9. This is going to be hinge, and we have this 1, 3, 2, and 3, 1.4 and 3, 1.4, and then this is 3. Okay, this is A, this is B, this is C, this is D, this is E, and this is F. Okay, let me have the dead load uniformly distributed for 10 kilonewton per meter. That is the cell weight of the beam. And then let me have the live load that's uniformly distributed, again 10 kilonewton per meter. This is going to be depend on this is going to be along the length of the beam. For example, this dead load is going to be anyway along the length. Okay, it will cover this back one, but this one will have the shape depend on the influence, and since what we have the influence positive is larger than influence of negative, so this one will have 10 kilonewton. Okay, like this. Okay, And later, let we have the live load that is going to be concentrated load of 100 kilonewton, maybe the wheel load. Okay, this one we're going to put it at what? At the point of the maximum coordinate, at the maximum influence. So we must put it in the F. That is going to be the F. Okay, and then we have this one for 100 kilonewton. We have this one for 10 kilonewton per meter, and we have this one for 10 kilonewton per meter, and then we will have maximum of C sub y. Okay, we compute maximum of C sub y. Can you? Okay, we have 100 kilonewton. That is the point load. The 100 kilonewton gonna time this one, gonna time 7.5, gonna time 1.4. Okay, and then what we have is this portion is in the positive. So this portion is has the positive influence. So we have plus, this is what 10 and 10 is going to be 20 kilonewton per meter. And then it's going to have 1/2. This length is going to be what? How many? 3, 2, 5. That is going to be 10. And then it's going to have this one is have 1.4. And you put them together. Not enough. That is this portion that is going to be provide the negative effect to our C sub y. So minus what? This one 10 kilonewton per meter, and times this one negative area, 1/2 of what? Of the length from here to here is 5 meter, and times this one for 1.4. Okay, if you push them together, you supposed to get this one for 245 kilonewton. Okay, you guys can compute it. I know that. And then if you go a little bit further, they ask us to find the maximum C sub y and maximum M sub e. Okay, maximum C sub y is 245 kilonewton. The M sub e. M sub e is what? No, M sub b. M sub b. This is wrong. M sub b. M sub b is here. M sub b is here, right? M sub b is here, right? Okay. By doing this, just project everything to be here. So our beam gonna be this way. Just put them together. And then now we have the influence only in the negative area. So this is going to be the same, and we have this one for hinge and this one for hinge. We have only the negative, but even though we have the negative, since the dead load always goes along the length, so by this one we just put the dead load W 10 kilonewton per meter along it. However, since this one produces the negative in this area, so the live load W just put it in this area, 10 kilonewton per meter. The point load, the live load, that is the point load, that's gonna put at the maximum value of it. So just put this one over here. That is 100 kilonewton. So maximum M sub, this time M sub B is going to be 100 times what? 100 times this one times minus 3. And then we have this one going to go together plus this combination is 20 kilonewton per meter. Gonna time what? 1/2 of the length here of 5 meter, and this one is going to be -3. And then plus for this portion, even though we put the load here, that is going to be 0. Okay, so this one going to be -450 kilonewton meter. So that is what we have for this one. Put the negative here also for the last example. Next lecture, we will talking about the absolute maximum moment and absolute maximum shear for our problem. Thank you very much. Today, I am supposed to finish my lecture here, and hope you guys have a time to review everything. We're going to have the midterm examination on this coming Sunday. Okay, bye bye all. Thank you very much.